What's going on, everyone? I'm Brian Thornberry, and today I'm going to teach you how to take your deep Q learning network and train it on Atari games. If you've been following along, this is the second part in the series, and we're going to build on the code from the last video where we created our very first deep Q learning network and trained it on the cartpole environment. If you haven't been following along in the series, then go ahead and click the link in the description below to get the starter code for this project.
Got it. Okay, come on. Okay. Here we go. Oh, all right. Well, that's me playing Breakout, and you can see I'm really not good at it at all. Let's go ahead and train up an AI on this game and see if we can make it even better than I am. Okay, so before we dive into the code, let's come take a quick look at the paper. This is the same paper from the last video, Human Level Control Through Deep Reinforcement Learning. We need to come take a look at some of the pre-processing steps they're doing on the Atari environment, because we need to take some of those same pre-processing steps. So if we scroll down all the way to the methods section, we can take a look at a few of the pre-processing steps that we'll need. First of all, they convert the output image of the environment to grayscale and then rescale it to an 84 by 84 image, greatly reducing the size from 210 by 160. Then they stack each of the last 4 frames the agent has seen into a single observation. This allows the agent to take information from each of those frames when it's making a decision on an action. If we scroll down a little further, we can see that they clip all positive and negative rewards between 1 and -1. They also skip frames so that the agent only interacts with every 4th frame of the environment and repeats its last action on those skipped frames. There's also one more pre-processing step that I haven't found in the text, but is only in the hyperparameters section, and that is the no-op max. Essentially, this forces the agent to take up to this many, so 30, do-nothing actions at the beginning of each episode, adding stochasticity and randomness to each episode of the environment. Okay, to quickly review, our pre-processing steps are skipping the frames, grayscale and rescale 84 by 84, reward clipping between -1 and 1, frame stacking, k equals 4 means that we stack 4 frames at a time, and we take up to 30 no-op actions at the start of each episode. The code to actually perform these pre-processing steps I provided in the starter code for this video. So please go ahead and click the link in the description below, download the starter code, and let's go ahead and dive right into the code. Okay, let's go ahead and open up our project. If you're continuing on from the first video in this series, this DQN.py file is the ending code from that video. When you download the starter code and extract the zip file, you should see a directory like this, with the baselines wrappers package, DQN.py, messagepack numpy.py, and PyTorch wrappers.py. I'll go ahead and explain what each of these files are in just a moment. First, we need to get our dependencies installed. If you haven't followed along from the first video in this series, you need to set up this virtual environment, and then you need to run pip install gym-torch, like you see here in the terminal below. If I go ahead and run it, you can see I already have those installed in the virtual environment. Now, if you're on Ubuntu, like I am here, you need to install a couple system packages before we install the Python dependencies for this project. Those system packages are zlib1-dev, which is a compression library, and cmake. Both of these system dependencies are required for the install of the Gym Atari package, which allows us to create environments for our agent of Atari games. Now, once you have those system dependencies installed, we need to install our Python dependencies for this project. Go ahead and run pip install messagepack is equal 1.0.2 like you see here. We're using the specific version because the first time I installed this, it installed an older version, and I'm not sure why. Gym Atari, as you see here, and tensorboard. We're going to be using tensorboard in this project so that we can observe graphs of how our agent improves over time and compare that with the graphs our improved agents create in subsequent videos in this series. Go ahead and run that, and you can see I already have all these installed. Now our system dependencies are installed, and let me go over the items included in the starter code for this project. First of all, we have the baselines wrappers package. This contains a number of environment wrappers copied over from OpenAI baselines and slightly modified for this project. We're going to be using a lot of these wrappers, but there are a few here that we're not going to use. Then we have the messagepack numpy.py. This is copied from a GitHub repository and adds the ability to serialize NumPy arrays using MessagePack. We'll be going into that a little bit later in the project. And then we have the PyTorch wrappers.py file. I provided this file to adapt many of the environment wrappers from OpenAI baselines to PyTorch, and also included a couple other environment wrappers necessary. How we use these files will become apparent as we start coding. Now you might be wondering, is it okay to just copy this code into the project like this? And yes, it is. As you can see here, OpenAI Baselines is released underneath the MIT license, which is a very permissive open source license, which allows me to provide these wrappers in the starter code for this project. And you can see that the MessagePack NumPy repository is also provided under a very permissive open source license. So in both cases, it's okay for us to put this code in our project. As we begin, let's go over the steps we'll need to do in order to make this Q network play Atari games. So we've already downloaded the starter code and installed our dependencies. Next, we're going to be setting up the Atari Gym environment. Then we'll be switching to a batched environment so we can run multiple instances of the environment in parallel and speed up our training a little bit. The agent will be using a convolutional neural network instead of a simple multi-layer perceptron as we did in the previous video. We're going to put in the code to save and load the model. The training for these Atari games can take a long time, up to 12 hours or even days. So we're going to want to be able to save the model and load it later to watch it play the game. We're going to set up logging to the tensorboard server so we can have graphs of our agent's improvement over time and compare those graphs with improved versions of the Q network in our later videos. We're going to add in support for training on the GPU. Training on the GPU can considerably speed up our training time for the Q network. However, this is not a requirement. If you don't have a GPU, don't worry about it. The code will still work fine running on your CPU. Then, we're going to train on Atari Breakout. I selected this game because it's a game I've never been good at and I want to see the AI play it really well. Then we're going to make a script so that we can load up our model and watch the AI play the game whenever we want. Okay, let's get started coding. Okay, so the first thing we need to do is change our environment from the cartpole environment to the Atari environment. And we do that using the make Atari DeepMind function included in the starter code. And this is a part of the PyTorch wrappers.py file. And we can see here, if you go over each of these, it applies all of the pre-processing steps we talked about earlier to the environment before our agent sees the observation. Gym wrappers are a really convenient way of doing this. I want to take a moment to point out the transpose image obs wrapper right here. This wasn't included in our pre-processing steps, but is necessary in order to convert the output image of the environment to the format required by the PyTorch convolutional network implementation. Most TensorFlow convolutional network implementations use a format called HWC, which is height, width, channel. However, PyTorch uses the format called CHW, channel, height, width. CHW and HWC refer to the order of the dimensions with respect to the components of the image. For example, CHW is channel height width. So the first dimension of the image refers to the channel, RGB, where the second dimension refers to the height, so the Y pixels, and the W refers to the width, the X pixels. HWC is the same thing, just in a different order. This wrapper will transpose the tensor so that the components are in the order expected by the PyTorch convolutional network. To quickly note one more thing, the frame stack operation is not included in the make Atari DeepMind function. We'll need to include that a little bit later, and I'll explain the reasoning for that in a moment. Okay, back to our main file here. Let's go ahead and import this make Atari DeepMind function. PyCharm is great for doing the automatic imports. Now we're going to set up a batched environment, which will allow us to run multiple instances of the game in parallel. We do this using the vecenv wrappers I've included as a part of the starter code. Now we'll need to change this to a lambda function, and we'll call it makeenv instead, because that's what the vecenv expects in its first parameter. So we're just going to go ahead and say make env. Note that I'm not calling the function, but we're passing the function in, and we're going to create num envs, number of different environments. So let's go ahead and create this up here. and this is going to be 4. And this is actually important. You might be thinking, well, let's just boost this up to get more parallelism. But your agent will also interact with the environment this many steps in between gradient steps. And the paper specifies 4 as the number of steps we need to take in between gradient steps when training on Atari games. So coming back down, let's just import the dummy vec.env. And let's delete this old cartpole line. We're also going to add a commented line here. Let me just put this there and then I'll explain it. This is the subproc vec.env. So let me explain why we're commenting this out. The dummy vec.env runs each of the environments in sequence, so we actually don't gain from parallelism here. But the subproc vec.env will step each of the environments in parallel so we can gain from using multiple cores at one time. Stack traces can get a little convoluted when we're using the subproc vec.env, so we want to do all of our debugging up front with the dummy vec.env, and we'll come and change this to the subproc when we're ready to do real training. Now, there's a number of changes we need to make in our code as a result of switching to a batched environment. Everything returned from a batched environment has a batch dimension, so we can no longer operate in the singular, as you'll see in just a moment. So let's scroll down here to where we're initializing our replay buffer. We no longer want to sample just one action. We want to sample multiple actions at one time, one for each environment running inside of our vec.env. We do that just like this. Pretty simple there. And we need to come and change this to plural. Make sure we're using plural everywhere. All of the elements returned by env.step and env.reset also have a batch dimension, so we need to change all of these to be in the plural. And make sure to set our new ops correctly. We now have multiple transitions included in every single step of the environment. So we need to construct each transition and add that to the replay buffer separately. And let me just type this out. We're going to want to move this assignment here outside of our for loop. So we do that after, and then right here, now we're all ready to go. So now we've zipped up each of the components of our transitions with a batch dimension and pulled out each of the elements we need to construct a single transition separately. We construct that transition and append it to the replay buffer as before. Now, this part where we're saying if done, reset the observation, we no longer need to have that. And the reasoning is because the dummy vec.env and the subproc vec.env both reset the environment when it's done for us. So we don't need to worry about that at all. So now we need to come down and make all the same changes in our main training loop. We're going to copy this right here and overwrite what we previously had right here. Note that we're overriding our episode reward tracking because we're going to be using a different method altogether. We need to set this to actions, and we'll come and change our act function in just a moment here. And we're going to copy this line right here where we're sampling multiple actions at once and put it right here for when we are taking random actions according to our epsilon greedy policy. We need to remove this whole section where we were watching the cart pull agent play when it was done. We're going to add a whole new script to watch the agent play after we're done changing up the Q network code. Now we're going to go ahead and change the act function so that we get multiple actions out at one time. As a result of that, we're going to need to also pass in the epsilon. And it looks like we still have obs here, so we've neglected to change this to obses. So let's go ahead and do that real quick. We get obses from the env reset, and we pass that into the act function. Now coming up to the act function, we add epsilon as a parameter. We change obs to obses. Go ahead and change this first line to be plural as well. Get rid of the unsqueezed 0 here. We no longer need that since we have a real batch dimension, and change this to the plural obses t. We no longer have just one index, but we have multiple indices. We remove this subscript 0 here, propagate that naming change, no longer .item, we have .toList to get the actual list of actions, no longer a single action. And now we need to perform the epsilon greedy policy to select a random action with probability epsilon inside of this act function. Let me quickly type that up and then explain it. So all we do is iterate through the index of each of the actions. We get a random sample, and if that random sample is less than or equal to epsilon, we replace that action with a completely random action. Now you'll notice we have the self.num actions here, but we don't actually have that in our class. We need to come up to the top and assign that to env.actionspace.n. Now we need to come back down to our main training loop. Since we're performing the epsilon greedy policy inside of our act function, this entire if statement is no longer needed. Now you may have noticed that some of our new variable names, such as obses, are conflicting with previous variable names we've used in our gradient step. So what we're going to do, we're going to copy this entire portion, starting with the obses np.asArray, all the way down to the gradient descent step. Cut that out, clean that up a little bit, and then we're going to come back up here, and we're going to create a function called compute loss on our network class. You can see that we need the transitions to be passed in, so we'll create an argument for the transitions. We also need to create an argument for our target net. Now let's change this to self, since we will be calling this on the online net, and let's remember to return the loss. Now we scroll back down to our gradient descent step, and right here we get the loss by calling the compute loss function on the online net, just like so. Now there's only one more change we need to make. We come up to our epsilon where we're interpolating the value based off of the current step. We need to multiply this by the number of environments, because each step in this training loop means we've stepped this many environments, so we've actually taken that many real steps. At this point, we've successfully set up the environment for our Atari game and switched everything over to using the vec.env. So we're going to go ahead and run a smoke test to make sure everything is still working properly. Looks like we made a small mistake here. We need to add the range function. We cannot just iterate over a number. Run another smoke test. Okay, and it looks like we made another small mistake here, and that's because the input to this neural network is a three-dimensional tensor, no longer a one-dimensional tensor like we had in CartPole. So what we need to do is actually add a flattening layer here. In a moment, we'll be replacing the sequential network with a convolutional neural network. Now let's run another smoke test. Okay, and it looks like we made another small mistake. Now, most people would probably edit out these small mistakes, but I find that they're so common when I'm implementing AI that it's really important that you can see what kind of mistakes you can easily make and keep awareness for yourself so that you really try hard not to make these mistakes. In some cases, these mistakes can be really, really difficult to find. So you can see that we accidentally added the actions instead of action to the transition buffer. We need to come down here and fix that here as well. And now we'll run another smoke test. And we can see that we're getting logging. It appears to be working. Stop that, move this terminal out of the way. And now we're going to change the way we're tracking the episode stats since we're no longer even using the reward buffer. So we want to come up here and change episode reward to episode count so we can keep track of how many episodes our agent has completed in the environment. We're going to change reward buffer to be called ep.infos buffer, which stands for episode infos, and you'll see why we're using that name in just a moment. Get rid of this 0.0 here and leave the rest the same. Now we come down here to our main training loop, and we need to change this underscore here, which is the info dictionary being returned by the env.step, and this is going to be a list of dictionaries. Now we need to make a small change to our makeenv function, and we're going to add the monitor. And right here, and we add the parameter allow early resets equals true. Go ahead and import that, and if you're using PyCharm like I am, you're going to get multiple options here. Just go ahead and take the baseline's wrappers, the one I included in the starter code. Now the monitor will add information to the info dictionary returned by env.step at the end of an episode with data for the reward and length of that episode. So now we need to come down to our main training loop and replace this underscore with infos, which is going to be a list of info dictionaries. We come right here down to our transition loop, and we're going to add in another element to our zip here, which is the infos. Now, if the episode is done, we will add that info to our ep.infos buffer, like so. Also, we're going to increment our episode count. Now, inside of this info dictionary, there is a sub item called episode. And that is actually the one that we want, since it will include the reward and length of the episode. Now we scroll down to our logging section. I'm going to type out the logging changes and then explain them after I'm done. Okay, so you can quickly see what we did here. Inside of the epinfo's buffer, each element is its own dictionary. Inside those dictionaries, there's a key called R, which has a reward for that episode. So we take the mean of all those rewards inside the epinfo's buffer to get the reward mean. The OR 0 just prevents us from having a NaN or a NaN here. And we do the same thing for the key L in the epinfo's buffer, which is the length of that episode measured in steps. Both of these elements, the R and the L, are added by the monitor we just created a little bit earlier. Now remember, a little bit earlier I mentioned that we had set up all the pre-processing except for the frame stacking. Now we need to come back up and set up the frame stacking. To do that, we're going to use a special wrapper called batched PyTorch frame stack. We're going to change our dummy vec env, the variable, to be called vec env instead. That way we can easily differentiate. The batched PyTorch framestack wrapper is a special kind of wrapper called a vec env wrapper. So we don't actually put it in the make env function like we're doing with our other wrappers. It wraps the vec env directly. Now let's import this real quick. Comes from the PyTorch wrappers file. And then let's go ahead and take a quick look at this so we can understand why we're wrapping the vec env rather than the regular env. So the batched PyTorch framestack wrapper stacks the frames for each observation without duplicating frames between observations. What I mean is if we have the agent interacting with the environment at step 1 and it sees all the last 4 frames, and then it interacts at step 2 and it gets the previous frames from step 1 inside of the observation because the frames are stacked, we don't duplicate the memory for those frames inside of our replay buffer. And in order to do that, we're using a special class here called PyTorch lazy frames. If you want to, you can dig into the implementation of this to understand exactly how it works. But all we really need to understand is that the observation being returned by batched PyTorch framestack is a list of PyTorch lazy frames rather than a NumPy array. Coming back to our DQN.py file, because we're no longer getting a NumPy array back from our environment as the observation, we need to make a couple changes to the way we're handling the observations when we use them. The changes are pretty simple and we only need to make them in 2 spots. So first we come down here to our main training loop where we're calling onlinenet.act. Let me type this out and then I'll explain what it is. Okay, let's quickly import the PyTorch lazy frames from PyTorch wrappers and let me explain this. So what we're doing, we're checking the observation returned from the first of our batched environments and checking if it's a PyTorch lazy frames. Remember that I said that the environment will return now a list of PyTorch lazy frames, one for each environment in the vec env, corresponding to our num env's constant. If we have PyTorch lazy frames, we actually need to convert that into a NumPy array before we pass that into our onlinenet.act function. And we do that right here by getting each of the frames as a NumPy array using this convenience function getFrames on PyTorch lazy frames, turning that into a list, and then calling np.stack to create a NumPy array out of that list. Now with this new NumPy array, we can call onlinenet.act as we did before. We put the else in here in case we disable our frame stack so that we can still run this code. Now there's one more spot where we need to make a similar change. So let's go ahead and copy this if line here and scroll back up to our compute loss function on our network class. The first thing we need to do is remove the np.asArray call on obses and on new obses. Both of these are going to be lists of PyTorch lazy frames, and np.asArray won't turn them into a NumPy array how we're expecting. Next, we paste that line from above. If is instance obses 0 PyTorch lazy frames, we're checking if we're using the lazy frames the same way as before. And if we are, we go ahead and create our NumPy arrays from our lazy frames just the same way as before. Okay, now that we have that typed out, make sure you include the else in case, once again, we removed our batched frame stack. That should be it for the changes we need to make for the batch frame stack. So we're going to go ahead, open up our terminal and run another smoke test here. And it appears to be working, so we're going to go ahead and exit out of that. Let's get this terminal out of the way. Now the next step is to come up here and change out our sequential network with a convolutional neural network. So I'm going to go ahead and type out this convolutional neural network function and then talk about it when I'm done. Okay, let's go over what's going on inside of this nature CNN function. So this is the convolutional neural network architecture that was defined inside of the paper, which was published in the Nature journal, which is why it's usually called the Nature CNN. First, we get the number of input channels, which, since we're using the CHW format for our input image, is the number of elements in the first dimension of our observation space. Next, we set up our actual sequential convolutional neural network using the nn.conv2d function included as a part of PyTorch. It appears I made a small mistake here. This n input channels needs to be replaced with depths 0, and this one with depths 1. So these lines right here set up the architecture as defined in the paper with ReLU activations in between each convolutional layer and a final flattening layer at the end, which allows us to pass the output of that convolutional neural network into a final fully connected linear layer with another ReLU activation at the end. Now this little trick right here where we compute the number of input units to our final linear layer is something I picked up while browsing open source for DQN implementations on the internet, and it actually does a forward pass through the CNN and looks at the output shape of the tensor. This is a really nice trick and I like it a lot. So now we come down to our network class. We're going to replace self.net. We're going to go ahead and create another one called convnet. And we're going to call the nature CNN function, passing in our env.observation space and leaving the rest of the parameters as default. And then we replace self.net with a final sequential network, taking in the output of the convnet, passing it to another linear layer with 512 inputs, and self.num actions output. And this needs to be nn. Now we've switched out the network for a convolutional neural network. Let's go ahead and run a smoke test and make sure everything is still working. And we can get rid of this line right here. Open up our terminal, run the program, and it appears to be working. So we'll go ahead and close that. And you can see I'm getting this warning here, could not initialize nn pack. Don't worry about that. That's because I'm using a computer with 2 CPUs. So we're going to go ahead and minimize this terminal. So now we're going to add methods so we can save our model to a file and load it up later to watch it play the game. Before we do that, we need to scroll up and make a quick change. We're going to import message pack, and we're going to import from message pack numpy, import patch as message pack numpy patch, just so we don't have a random variable called patch floating around. We're going to go ahead and call that message pack numpy.patch. And what this does, this goes ahead and patches the primary methods we're going to be using on message pack to support numpy arrays. That way we can save our model parameters using message pack. So we scroll down to our network class all the way to the bottom, and we're going to add the save function. Now I'm going to type this out and then explain what's going on. Okay, now I have that typed out. Let's quickly come up here and import OS. Scrolling back down. Okay, so the first thing we do in this state function is convert the state dict to have values with a NumPy array rather than as PyTorch tensors, so we can actually save them. We call .detach and then .cpu. The reason we're calling .cpu here is because later we'll be moving these tensors onto the GPU, so we first need to move them back into main memory before we can convert them to a NumPy array. You don't need to worry about that for the moment, but it's good to know. At that point, we serialize our parameter dictionary into the params data variable using message_pack. Now you might be wondering at this point, why are we using message_pack when we can just use pickle? And pickle would work just fine. I argued with myself before making this video if it was really necessary to use message_pack. But the problem with pickle is that anytime you save a pickle file, that file becomes a constant security threat. That file could be changed at any time, and if you were to save it on a USB drive, could be easily accessed by someone other than yourself. Then when you would go up and load that file at any time in the future after it was changed, it could be executing any arbitrary Python code. And that's a huge security vulnerability that never goes away that you create yourself. So instead, we create message_pack, which doesn't have that type of explicit vulnerability. Next, we make sure our save directory exists, open up the file. Very important here that you open it up as a binary file using the WB mode here, and then we write our params data. Now I'm going to quickly type up the load function. It's going to look very similar, and I'll quickly explain that as well. Okay, very similar load function here. We make sure the file exists, and if not, we throw file not found error. We open up the file, once again in binary mode, deserialize it using message_pack.loads. Then we convert each of the keys of the dictionary back into a PyTorch tensor and then load those params into our model. Now it's important to note here that we do not need to save the parameters of our target network, since the online network is the one that makes all the decision making and the target network is only interesting during training time. Even if we were restarting training, we still would not need to save the target network. We could just set its parameters equal to the online network like we already do at the beginning of the new training run. Now we're going to quickly add some code to automatically save our model at a specified interval, so we have a checkpoint. Scroll up to our constants. We're going to add two constants here, save path, and we're just going to make this ./Atari model.pack, the .pack standing for message pack, and we create another one, save interval. Set that to 10,000. Come back down here to where we have our logging step. I'm going to create a new one called the save step. And if step mod save interval is equal to 0, then save our model. And that's it. I like to add a little print statement here though, so that I know that it's actually saving the model. And one more thing, we actually don't want to run this when step is equal to 0. Now that we have the saving handled, we're going to go ahead and add in tensorboard logging. Remember, tensorboard will allow us to see graphs of how our agent improves over time. So we come right here, right above episode count, and we're going to create what's called a summary writer. Summary writer is an included component in PyTorch that we just need to import. So from torch.utils.tensorboard, we get summary writer. And let's go ahead and create our logdir constant. Scroll up to our constants. We're going to set our logdir equal to ./logs/Atari vanilla. And the reason we're calling it vanilla is because we're going to create other log directories for our improved versions of DQN in the other videos of this series, and we can compare how they improve over the life of their training. Now we scroll back down to our logging section, and in this point, we're going to take this 1000 and we're going to replace this with log interval. Scroll back up to our constants real quick and create that and set it to 1000. Come back down to our logging step, and here is where we're going to start adding values to our tensorboard graphs. This is very simple to do using the summary_writer.addScalar method. Here we're going to add the average reward at each logging step, like so. So you can see first we give the name to the scalar, and all values added with the same name will be included in the same graph. And then we set the value of the scalar to root mean, which is essentially the y-axis on that graph. And we set the global step to our step, which is essentially the x-axis on that graph. Now I'm going to type out a few more of these real quick and then quickly go over them. Now, these are pretty much identical to what we're logging with our print statements above. The only difference is that now we're adding them to our tensorboard graphs. So we're going to go ahead and do a quick smoke test to make sure this is working and actually look at these tensorboard graphs. So what we want to do is come up here and change our log interval to a small value, like 10. Open up our terminal, run the function, and let it log a few times. Okay, great. We let it log about 11 times. Now running TensorBoard is very simple since we've installed the TensorBoard Python package inside of this virtual environment. All we do is in our terminal type in TensorBoard --logdir./logs. Run that. Once it's started, we navigate to this URL in our browser. You can see I've navigated here and we can take a look at what these graphs are going to look like. We can see the average episode length was going up a small at a time. We can smooth out these graphs with the smoothing, and TensorBoard has a lot of other great features that you can take advantage of. I encourage you to explore them, and you can do a lot more with the summary writer than just creating these graphs. Okay, let's exit out of that, close TensorBoard, and get this terminal out of the way. Now we're going to come into our logs directory here and delete those logs we just created, the TensorBoard logs. And the reason is that if we were to run the script again without deleting these logs, it would restart from step 0 and the TensorBoard graph would get really wacky. You can go ahead and try it if you like and take a look at the result. I like to just come in here and delete this between runs. You could make this automated, but I find that I could easily forget about logs that I want to keep that way. Now we're going to be moving on to our final coding portion before we're ready to train on the Atari environment. That final step is adding support for training on the GPU. Certain GPUs can be much faster for computing the tensors than our CPU. First things first, we come down to our make_env function right here. Right above this, we're going to create a variable called device, and I'm just going to type this out real quick. Okay, so what this does, this is saying, let's use the GPU, the first GPU, if a GPU is available, otherwise just stick with the CPU. So if you don't have a GPU, you could still add this line in and the code would still work fine, and make the rest of the changes we're about to be making and the code will still work fine on your CPU. Okay, so first thing, we come down here and we want to put our actual models on the GPU. And we do that using this .to method, and we call .to device. Do the same thing for our target network. Now that our models are on the device, we need to make sure that all of our tensors are on the device. So what we're going to do, we're just going to go ahead and search for as tensor. And anywhere where we see as tensor, except inside of this nature CNN function, this is a notable exception because the model will still be on the CPU when we're actually calling this function. So we come down to the next one, and we want to make sure we add in right here, comma device equals self.device, which reminds me, we need to pass in the device to the network class here. So we're going to do that. We're going to set self.device equals device. We're going to come down to where we're instantiating our networks to fix that real quick. And that's right here. We go ahead and set that to the device variable we already created. Okay, now let's come back up to the network and search for as tensor once more. Okay, we're on our second one here. We already set that one. And right here, we need to do the same thing. So let's just copy that and put that inside of all these as tensor calls right here. Okay, and let's see if we have any more. We've got one more right here in our load function. We do need to put it there as well. Okay, and that's all of them. So that's it for making this run on the GPU. Pretty simple. PyTorch has these really convenient methods and handles most of the complexity for us. So let's go ahead and open up back our terminal and run another smoke test to make sure everything is working fine again. Okay, and it appears to be working well and actually a little bit faster as we can see. So let's get this terminal out of the way. The very last change before we're ready to start training, we need to change up these hyperparameters to mask the hyperparameters from the paper. So we're going to change our buffer size to 1 million. We can do that. This right here, int 1e6. We're going to change our min replay size to 50,000. We're going to change our epsilon n to 0.1, our epsilon decay to 1 million. Target update frequency to 10,000, leave number of n's at 4, and we actually need to add in another parameter here, which is our learning rate. We're going to set that to 2.5 e negative 4. And I guess we didn't do this earlier. We need to come down to our optimizer, which is right here, and set that right there. Okay, scrolling back up to our hyperparameters, we're going to change our log interval from 10, where we had it set really low, up to about 1,000. And the rest of this is looking really good. We're ready to start training. So training this is going to take a number of hours. I'm going to go ahead and run the training and cut back to when it's done, and we can take a look at the results. Okay, so I just finished the training and it ran for, let's see, you can see here, it changes to wall. I've got the tensorboard open up here. And it looks like it ran for about 26.5 hours. Now I let this run for a long time, but you can see that we reached the peak reward sometime around 3 hours in. And these are actually not really exciting results, and there's a number of reasons for that I'm going to address in the next video, which is going to be about how to improve these results, but it's actually still very exciting to watch. So we can see here that the average reward, this went about for about 3.1 million steps. So that's actually 12 million frames of the actual environment, which is well over the 10 million frames they trained on in the paper. So we can see that the highest average reward was actually a little higher than 4. And this is actually the reward per life. So to put this in context, we need to multiply it by 5. And the average score the agent is able to attain in one episode is somewhere around 20 on the highest side. So we can make this a little bit bigger and take a look at kind of what's going on over time. And like I said, these are not really exciting results. I expected to see better, but we're going to address why this happened in the next video and improve these results even more. Okay, so let's close up tensorboard here and just watch it play. So I created this observe script, and I was going to go over this, but I've just decided to include it in the starter code now, since it's mostly just copying, pasting little bits from our training code, and there's really not too much to learn here. One thing that I did find specific to the Atari environments was that the agent needs to do the fire action at the beginning of every episode, or else it just stays in this frozen state. And the agent, for some reason, was not always doing that fire action, so it was just sitting there and not even actually playing the game. So I added in this little if beginning episode, we just do the fire action. And that's just a little workaround for the issue. Okay, so let's go ahead and run the script and watch the agent play. And we can see that it actually does pretty good. It's certainly a lot better than I am. Sure, it misses the ball sometimes and it kind of takes some weird actions every now and then. And that's what we're going to be addressing in the next video. We're going to get this score up a lot higher. Even though we want the score to be higher, I still think this is a really exciting result because, I mean, it's definitely better than I am. So if you followed along this far, thanks for watching. Remember to like and subscribe, especially if you want to learn more about AI. We're going to have more videos on DeepQ networks coming up in the future. We're going to be going all the way until we've implemented the popular and sophisticated rainbow algorithm. After that, I'll be doing tutorials on even more reinforcement learning algorithms. Thanks for watching and have a great day.